as a next step, and we already calculated for ground state. Let's consider for the first excited state. Two particles excited state. Excited state means that the first here is the E1 and E2 and like this, and the first state is 켜졌어요. 예. Yeah, first state is Na equal to 1, and the first excited state means that the second case is the 2. It is a first excited state, first excited, and the other particle is the ground state. So in this case, energy 1, 2 is that the first particle E1, the second particle is E2. So in here in the spin zero boson case, also we already know that the total wave function for 1, 2, it is a symmetric wave function. So in the spin part is a 0, 0. It is a symmetric spin state. So the spatial wave function should be symmetric. And the psi 1, 2, and the x1 and x2 should be symmetric. And the explicit form is that the 1 over square root 2 and the phi 1 x1 particle and the quantum number 1 and x2 particle quantum number 2 and the plus when we exchange with the two particles and the phi 1 x2 and the phi 2 x1, it is symmetric spin function, symmetric spatial wave function, and also spin part also symmetric. And then the fermion case, spin 1/2 fermion case, then it should be total wave function for 1, 2 particle in the fermion should be antisymmetric. Antisymmetric case. So first thing is the spin singlet state. Spin singlet, spin up and down. So it is antisymmetric because it is in uncoupled basis. It is a spin 1/2 and spin 1/2 and 0, 0. In other words, it is a combination between the spin up and down and minus in the down up. It is antisymmetric spin function. So and the total wave function should be, because spin part is antisymmetric, so and the spatial part should be symmetric, and spatial part should be symmetric, and x1 and x2, and the spin part is antisymmetric. So it is 1 over square root 2. Symmetric means that x1 particle at x1 quantum number 1 and x2 particle quantum number 2, and plus x2 particle at quantum number 1 and x1 particle at quantum number 2 and the spin state 0, 0. It is a spin singlet state. Then in the spin triplet state, and spin quantum number, spin is 1, magnetic quantum number 1, 0, minus 1, 3 possibilities. So it is in uncoupled basis, it is 1/2, and spin 1s and the magnetic quantum number m equal 1, 0, minus 1. three cases. So it is spin state is symmetric in triplet state. Symmetric spin triplet. So total wave function 1, 2 particle spin is symmetric, and therefore the special part should be antisymmetric. So psi 1, 2 it is antisymmetric, x1 and x2, and spin quantum state is 1m should be it is symmetric. So total wave function should be antisymmetric. Then it is 1 over square root 2, and phi 1 x1 and phi 2 x2, and minus phi 1 x2 phi 2 x1. It is minus sign. It is anti-symmetric wave function, and 1m like this. So anti-symmetric wave function is not zero here in this case. In the ground state case, and we should note that, and phi 1 x1 and phi 2 x2 is not equal to phi 1 x2 and phi 2 x1 in here, because it is 1 means that the ground state, and 2 means that the excited state, and two particle exchange is not identical. And so in the previous case for the ground state case, it is a one particle and the other particles, and it is a one case x1 x2, and the one case x2 x1 is identical, so there is no possibilities. But in this case, and it is not identical, because it is one first particle is a ground state and second particle at the excited state, and but in here, and the second particle is ground state and the first particle at excited state, so it is not zero. So it is not zero. So anti-symmetric wave function in the excited state can the finite probability. So when we think that when you draw the graph and the spin, for example, spin zero boson case, it is non-degenerate. Non-degenerated, but spin 1 total spin, it means the total spin fermion bosons. Bosons, there are two possibilities. One is the singlet state, and the other one is triplet state. And in ground state case, triplet state is not possible, but in excited state and triplet state can exist. So when you think that, if we think that the two energy level at the ground state, case, and the fermion, it is in boson case, bosonic particle can have the also same possibilities, same E1, E2, and ground state can be possible without spin. It is in wave function is that psi 1 1 and x1 and x2. It is the symmetric wave function, and spin is zero. But in fermion case, and the same spin triplet state is not possible. So only spin singlet state, spin up and down state should be considered, and the psi 1 1 and should be symmetric wave function, and x1 and x2, and spin state is anti-symmetric. It is a ground state. How about the excited state? First, the excited state. First, the excited state case, for example, in the boson case, here it is x1 particle at quantum number 1 and x2 particle quantum number 2, and also one particle at the ground state, the other particle in the first excited state, and it is a boson case only single, then there is no degeneracy. And psi 1, 2 symmetric, and x1 and x2, and it is a 0, 0. It is a bosonic case. How about the fermion? Fermion case, there are triplet state can be exist, and triplet state 1, 2, 3. Triplet state. One is that spin up state. It is a spin. It is a 1, 1 state, and also psi 1, 2, x1 and x2. Also, it is antisymmetric wave function, because spin is symmetric wave function, and also spin down down, it is a 1, -1 spin state, and also psi 1, 2, it is antisymmetric, x1 and x2, like this. But in other case, in the spin up and down state, but here 1, 0 state, it is a symmetric wave function. It is a superposition, and 1 over square root 2, and up and down plus down up spin configuration plus a spin configuration, because it is a symmetric. It is a triplet state, and it is a triplet, and the singlet state is singlet state case, singlet state, and same as down up combination, also same, but here, and the spin state is 0, 0. Spin state is 0, 0, and also wave function, because it is antisymmetric spin state, and 1, 2, it should be symmetric wave function, x1 and x2. And here, and it is spin vector, it is 1 over square root 2, and spin up down combined with minus down up. One characteristic of quantum mechanics is that superposition, and symmetric superposition and antisymmetric superposition is different physically, and the two particle superposition, spin up and down up combination is identical in classical point of view, but in quantum mechanics, and the symmetric superposition and antisymmetric superposition is different. And also in the energy case, and the first excited state, and the energy is that the E1 plus E2. Energy is that the E1 plus E2, and the ground state energy is that the 2E1 case. So in physical interpretation of the symmetric and antisymmetric case is that in bosonic particles, in bosons, wave function had a symmetric wave function. So in the phi 1 x1 and phi 2 x2 at, for example, x1 and x2, and it is a potential well. And when you combine with each other at the same state, and the probability distribution of two particles at x1 and x2 can close with each other at the same state, and the finite probability at x at the origin. But in fermion case, wave function is antisymmetric, and here, for example, at x1 is here, and x2 case then the antisymmetric wave function. So by superposition of two particles at the same quantum state, and the probability is 0 in the triplet state. So there is no probability of existing two particles in the same quantum state and the same position for fermions, especially in the ground state. That is the Pauli exclusion principle.